Well, thank you very much, Don, and thanks to all of you. It's certainly a pleasure to be back with so many friends and colleagues at the University of Maryland and also the University of Delaware at this event, and other universities represented as well. It's a particular pleasure to join my colleagues at the University of Maryland because I exploit so many of them in the White House. My deputy who leads the Environment Division at the Office of Science and Technology Policy is Steve Feder, the former Dean of the School of Public Affairs here. Dr. Jim Gates, a professor of theoretical physics here, is a member of the President's Council of Advisors on Science and Technology. I pick the brains of the likes of Don Bosch and Tony Genados on global change issues all the time. And so again, it's, as I've already said to a number of your officials around the coffee this morning, it's terrific to have universities of this caliber so close to Washington, D.C., where we in the full-time service of the government can take advantage of them. As for Don Langenberg's very generous introduction, it is certainly an honor to be giving the lecture named for him and his contributions to lifelong education. I do have to tell him, though, that the solutions to most of the problems he mentioned are the topic of a different lecture than the one I will give today. Today, as the slide indicates, I'm going to talk about coping with climate change issues in science, technology, and education, and I will be trying to cover quite a lot of ground. So for those of you for whom some of this goes by too quickly or you're sitting too far in the back to read all the slides, we will post this presentation on the OSTP website, www.ostp.gov, in the next 24 hours, so you can get at it for a closer look. But I want to start with what I see as the overarching questions in climate change science, in climate change policy, and in climate change education. And starting with climate change science, of course, the first question is, what do we know or think we know about climate change? The second question is, how and with what confidence do we know it? The third is, what more do we most need to know? And how and when can we know those additional things that we need to know? In climate change policy, of course, the key question is, what should we do and when should we do it? And at the intersection of science and policy, there is this question: how can the answers about the science better inform the answers that publics and policymakers embrace about what to do and when to do it? So let me start with the science questions. And I'll do this in terms of talking about 6 myths about the science. Number 1, that the Earth stopped warming in the last decade. Number 2, if it is warming, humans aren't the main cause. Number 3, a little warming won't hurt us anyway. Number 4, if there is any danger, it's far in the future. Number 5, the Climate Research Unit emails from the University of East Anglia and the mistakes disclosed in the reports of the Intergovernmental Panel on Climate Change showed that mainstream climate science is deeply flawed. And actually, I got rid of number 6 in trying to shorten this lecture a little bit, but we'll sneak number 6 into a later part of the talk anyway. Well, first, with respect to the question of whether the Earth is any longer warming, here's what thermometers say. These are the latest data from the Goddard Institute of Space Studies up through 2010. 2010 tied 2005 as the hottest year in the instrumental record, which goes back about 130 years now. That's the period over which thermometer measurements were widespread enough to meaningfully define a global average surface temperature, which is what this is. 2007 tied 1998 as the second hottest year. The 15 hottest years in that 130-year instrumental record have all occurred since 1990. If you want to look at a closer picture of the recent years, this is the period from 1980 to 2010. Some folks say, well, 1998 to 2008 was a period of no increase. You can sort of see where they get that, but it's a misreading of the naturally bumpy record. The trend continues upward, virtually unabated. And other climate indicators are changing apace. For example, you expect in a warmer world there to be more evaporation. What goes up must come down, so there's more precipitation. That's not true everywhere. Some places get drier, while some get wetter because of the complexities of the global climatological system. But on the average, it is getting wetter as expected. Glaciers are retreating almost everywhere in the world. This shows glaciers in the Himalaya, a particular glacier on Mount Everest northern slope, 1968 at the top, 2007 at the bottom. Arctic sea ice is both shrinking and thinning. The different colors here, the maroon is first-year ice, blue is second-year ice, green is older ice. You see the green shrinking drastically, even as the area also shrinks. 2009, the record up to that time, it looks like 2010 will be down there as well. Both Greenland and the Antarctic ice sheets are losing mass. The floating ice in the Arctic doesn't change sea level because it is floating ice, but this ice, when it melts, does raise sea level, Greenland and Antarctica. A few years ago, we weren't sure that Antarctica was losing mass. Now we are sure that it is. Sea level, of course, is rising, not only as a result of the mass loss from glaciers and the great land ice sheets, but also because of thermal expansion of seawaters. It gets warmer, it expands, sea level goes up, and you see that the recent observations are at the upper end of the projection, the projected range by the Intergovernmental Panel on Climate Change. In terms of whether or not we know humans are the primary cause of these alterations, this is the IPCC 2007 report's account of the overall magnitude of human versus natural influences on the climate over the last 250 years or so. This is what climate scientists call forcings, which literally means how hard you're pushing on the climate with one factor or another. They're measured in watts per square meter of alteration in the Earth's energy balance, averaged over the whole surface of the Earth, but you need not pay so much attention to that. It's the relative magnitudes here that are important in telling us about human versus other effects. And you see at the top the magnitudes of the effects of human emissions. Positive are warming influences, negative are cooling influences. And you see that the cooling influences of particles partly offset the warming influences of greenhouse gases and absorbing particles, but not by any means entirely. Land use changes are a small effect, and natural changes in the sunlight reaching the Earth over this period, a very small effect. Some of the skeptics will tell you they believe the sun is doing this and not human activity. If you look at the numbers, it just doesn't hold up. The influence of the sun over this period is about 30 times less than the warming influence of the greenhouse gases and absorbing particles. We know that the key greenhouse gas increases were caused by human activities. This shows at the top the carbon dioxide trace for the last 10,000 years and the last 250 years in the inset. Same thing for methane at the bottom. If you look at the 10,000-year record, you see the distinction between the slow natural variations in these concentrations and the extraordinarily sudden spike associated with large-scale human influences on the planet, and particularly the influences of combustion of fossil fuel, whose signal is unmistakable in the atmospheric concentrations of carbon-14 versus other carbon isotopes. This is what I call the fingerprint. This is a complex diagram, but it's extraordinary in its implications. At the top panel, one sees the best estimates of both human and natural forcings for the period of the instrumental record, the period in which we have thermometer records of the average temperature of the Earth. And so you see the top red line is all the greenhouse gases. The blue line oscillating downward is the effect of volcanic eruptions, which temporarily tend to cool the Earth because of reflecting particles injected into the stratosphere, other factors in between. And what you see in the bottom panel is what a state-of-the-art climate model says the global average temperature will do when it is fed those forcings from the top panel. In other words, when you feed our best climate models what we believe to be true about the forcings over this period, it reproduces with remarkable fidelity the observations, which are the blue asterisk, the observations over this period. It's very hard to look at this and conclude that we don't know what is driving the temperature changes that we are observing. Turn to the question of what harm can it do? Well, first of all, we need to understand that climate governs, and therefore altering climate will affect the availability of water, the productivity of our farms and forests and fisheries, the prevalence of oppressive heat and humidity, the formation and dispersion of air pollutants, the geography of disease, what pathogens and vectors of disease can live in what abundance for what time periods in what places, the damages that we have to expect from storms, floods, droughts, and wildfires, the property losses we need to expect from sea level rise, the amount of money we have to spend on engineered environments, air-conditioned spaces, dams, dikes, and so on, and of course the distribution and abundance of species of all kinds, those we hate and those we love. We are seeing harm, floods and droughts. This is data from a Chinese investigator at Tsinghua University, often called the MIT of China, showing that the 30-year weakening that has been observed in the East Asia monsoon, in which the Chinese climate models themselves attribute to global climate change, has altered the flow of moisture over China in a way that has produced increased flooding in the south and drought in the north, which is already causing serious impacts on agriculture in China. Wildfires. Wildfires in the western United States have gone up sixfold in the last 30 years, and there are similar trends in other fire-prone regions. Pest outbreaks. Pine bark beetles, for example, who got a longer breeding season courtesy of warming, have devastated trees weakened by heat and drought in Colorado and elsewhere in the western United States. Melting permafrost is damaging structures and roads and increasingly threatening pipelines across the far north. Coastal erosion from the combination of rising sea level and, in the far north as this, reduced protection from floating ice from the effect of waves is on the rise as well. In fact, we are seeing worldwide, variously and in different patterns in different places, increases in floods, wildfires, droughts, heat waves, pest outbreaks, coral bleaching events, the power of the strongest typhoons and hurricanes, the geographic range of tropical pathogens, and this is happening in patterns which very clearly, plausibly link climate change to these effects through theory, through models, and the observed fingerprints, the patterns in which these effects are occurring. And worse lies ahead, much worse lies ahead if business as usual persists. The left-hand part of these trajectories is the history, 1900 to 2000. The trajectories on the right are a variety of IPCC scenarios. The mid-range of that careens through the target now accepted not just by the European Union but by the United States, the target of holding the global average surface temperature increase to 2 degrees centigrade or 3.6 degrees Fahrenheit, careens through that target in about 2050 and goes far above it subsequently. What could this do? Well, this shows the percentage of summers expected to be warmer than the current 95th percentile of summers in a world which is warmed by 2 degrees centigrade, that target. And you see, over most of the world, 90% or more of the summers will be warmer than the current 95th percentile. That is, the hottest 5% of current summers will be absolutely the norm under that 2 degrees C warmer world.